Welcome to today's paper reading. Today's paper is titled, SaulLM-7B, a pioneering large language model for law. This paper introduces SaulLM-7B, a large language model specifically designed for the legal domain, published on the AR14 preprint by Pierre Colombo and colleagues from Equalel.ai and various academic institutions. This paper introduces SaulLM-7B, a large language model specifically designed for the legal domain. SaulLM-7B has 7 billion parameters and is the first LLM tailored for legal text comprehension and generation. It is based on the Mistral 7B architecture and is trained on an English legal corpus comprising over 30 billion tokens. The model demonstrates state-of-the-art proficiency in understanding and processing legal documents. Additionally, the authors present a novel instructional fine-tuning method using legal datasets to further enhance SaulLM-7B's performance in legal tasks. The model is released under the MIT license. This paper introduces the first publicly available legal large language model, LLM. The SaulLM-7B model is developed using extensive pre-training on specialized legal corpora from English-speaking jurisdictions. Legal text presents unique challenges due to its specialized vocabulary and evolving discourse. The contributions of this work include a family of legal LLMs, an improved evaluation protocol for legal LLMs, and open licensing to promote widespread adoption and innovation. The authors selected the Mistral 7B model, a 7 billion parameter open-source model known for its high performance across various benchmarks. To enhance its legal capabilities, they performed additional training focused on legal data, leveraging a meticulously curated corpus of 30 billion tokens. This approach offers scalability and independence from specific training data characteristics. Additionally, the model underwent instruction tuning, incorporating both generic and legal instructions to improve its ability to follow commands and handle legal queries effectively. Figure 1 illustrates the process for constructing SaulLM-7B, a specialized legal language model. The procedure involves leveraging legal datasets that are augmented with replay data and instruction datasets. During the fine-tuning stage, the instruction dataset is further enriched with specific legal instructions to enhance the model's performance in legal tasks. The authors collected legal text from various jurisdictions, focusing primarily on English language documents due to its global use in legal contexts. This collection includes data from the US, Europe, and Australia, resulting in a corpus of 30 billion tokens. The dataset composition involves combining previously available datasets like FreeLaw and Multilegal Pile, along with data scraped from publicly available web sources. A significant portion of the collected data required cleaning to remove artifacts such as page numbers, non-normalized Unicode characters, and broken lines of text. This was achieved through text normalization and perplexity filtering, ensuring high-quality text for further analysis. Table 1 provides an overview of the sources used for legal pre-training data, which includes a variety of legal texts from different jurisdictions such as the US, Europe, and Australia. The data underwent aggressive cleaning and deduplication processes, resulting in a 30 billion tokens dataset. This dataset captures the intricacies of legal language across regions and is essential for training models like SaulLM-7B Instruct. Table 2 presents the most frequently occurring 10 grams in the pre-training dataset, highlighting common legal terms and phrases. These 10 grams include phrases such as have been obvious to one of ordinary skill and rejected under 35 U.S.C. 103 as being unpatentable over, indicating a focus on patent law. The presence of these phrases underscores the dataset's structure and content, which is heavily influenced by legal documents. The evaluation of the model's legal abilities is conducted using 3 benchmarks. Firstly, perplexity is compared across 5 types of legal documents. Secondly, Legal Bench is enhanced with Legal Bench Instruct for a deeper evaluation. Thirdly, the legal section of Melo is used for additional insights. In the perplexity measurement, the adaptability of the backbones to legal documents is assessed using benchmark datasets spanning 4 distinct legal domains: contracts, judicial decisions, opinion text, and legislation. These datasets are up to date and sourced from various legal repositories. However, significant limitations were found in the original prompts of Legal Bench, leading to a substantial drop in performance. To remedy this, the prompts were refined by removing distracting few-shot examples and concluding with a specific instruction for the model to generate tags, thereby improving accuracy and readability. Figure 2 illustrates the process of converting dataset metadata into a natural conversation. Using a Reddit post classification example, the initial query and answer are reformulated into the first 3 turns of a conversation. The conversation is then continued by a user model, which generates relevant questions, and an assistant model that provides answers. Both the user and assistant models are instances of Mistral 7B Instruct. Table 3 presents an example from the curated Legal Bench Instruct dataset. The table highlights the process of manually curating and correcting typos in the original Legal Bench dataset. Specifically, it notes the removal of a few short examples that were found to distract LLMs of size 7B. This curation process aims to improve the clarity and effectiveness of the dataset for training and evaluating legal language models. In this section, we discuss the experimental setup and implementation details. Firstly, we compare the SaulLM-7B family with other state-of-the-art 7B and 13B open-source models, including variants of Mistral 7B and the Llama 2 family. For implementation, the code base leverages open-source frameworks, utilizing deep speed with flash attention, and is built on PyTorch with models hosted on the Hugging Face hub. In terms of compute resources, continuous pre-training is conducted using 256 MI250 AMD GPUs. Instruction fine-tuning is distributed across 16 MI250, and evaluation procedures are performed on a single MI250. Figure 3 illustrates the performance of various base models on the Legal Bench Instruct benchmark. Notably, SaulLM-7B, despite not being instruction fine-tuned, demonstrates significant improvements compared to other base models, including its initial checkpoint, Mistral 7B. Specifically, SaulLM-7B achieves a balanced accuracy of 0.38, while Llama 2-7B chat scores slightly higher at 0.39. This suggests that SaulLM-7B serves as a robust foundation for models with strong legal capabilities. In the Legal Bench Instruct evaluation, SaulLM-7B demonstrated significant improvements, particularly when combined with legal instruction fine-tuning, achieving a state-of-the-art average score of 0.61. On the Legal MLU benchmark, SaulLM-7B Instruct consistently outperformed other models, maintaining a 3 to 4 point advantage. The perplexity analysis further highlights SaulLM-7B's superior performance across various legal document types, with notable reductions in perplexity scores compared to both Mistral 7B and Llama 2-7B, especially in legislation documents. Figure 4 illustrates the significant improvements gained by starting the instruction fine-tuning process from the SaulLM-7B base model compared to the Mistral 7B. Notably, even with a generic instruction fine-tuning mix, without legal content, SaulLM-7B Gen demonstrates a marked superiority over its Mistral Instruct counterpart. The addition of legal instructions to the fine-tuning mix results in an even greater enhancement of performance. Figure 5 presents a comparison of Instruct models on the Legal Bench Instruct benchmark. SaulLM-7B Instruct is highlighted as the state-of-the-art model, significantly outperforming the best Mistral Instruct model by 6 absolute points. This figure underscores the superior performance of SaulLM-7B Instruct in legal instruction tasks, setting a new standard in the field. Figure 6 illustrates the performance of various Instruct models on the Legal MLU benchmark. Notably, SaulLM-7B Instruct demonstrates a significant advantage over the Mistral 7B Instruct v0.1 model, achieving an average absolute improvement of 5 points across all 3 tasks. This superior performance underscores SaulLM-7B Instruct's effectiveness as a robust foundation for building models tailored to legal workflows. Figure 7 illustrates the performance of SaulLM-7B Instruct in comparison to generic Instruct models on tasks requiring legal-specific knowledge. It shows that SaulLM-7B Instruct significantly outperforms on tasks like issue spotting, rule recall, interpretation, and rhetoric understanding, which are areas that demand deep legal expertise. However, It is noteworthy that Mistral Instruct surpasses SaulLM-7B Instruct on conclusion tasks, indicating that these tasks rely more on deductive reasoning rather than legal knowledge. This suggests a potential area for improvement by incorporating more deductive reasoning content into the training corpora. In this paper, the authors introduced SaulLM-7B, an open-source decoder model that achieves state-of-the-art performance in the legal domain. The model was fine-tuned on legal data and synthetic datasets, contributing to its advanced capabilities. Additionally, the authors have provided a clean version of Legal Bench and introduced new documents for perplexity measurement, further enhancing the model's utility. The model is released under the MIT license, aiming to contribute significantly to the open-source ecosystem and the broader legal research community. The authors acknowledge Gency for providing access to advanced computing resources. The SaulLM-7B model was trained on the Adastra platform, with initial experiments conducted on GeneSA. The use of high-performance computing resources was facilitated by GeneSA grants 101838, 103256, and 103,298, as well as Adastra grants C1615122, 14,770 Canadian dollars, and 15,031 Canadian dollars. Thank you for watching.